Okay, so I'd like to talk a little bit about what chapter 5 is about. The first part of the chapter, which we'll do this week, is directly proportional relationships. So, directly proportional relationships are a situation where when you have a graph and you plot the points are going to line up on a straight line so that when you connect the dots, you come up with a straight line. So just to back up, when we have a graph, we have an x-axis, which is the independent axis. So independent variable is going to be our x variable, and our dependent variable, dependent, is going to be our y variable, dependent. So it's very important to know what dependent and independent mean. Independent causes a dependent variable to change. Okay, so a change in x makes a change in y. So if we were to buy, say, shirts, say that our independent variable was the number of shirts that we decide to buy. So if we change the number of shirts that we buy, the total cost that we're going to pay for all those shirts is going to go up. So the cost depends on the number of shirts we buy. So that's how these two variables relate to one another. And this is always going to be on the horizontal axis, and our dependent or y variable is always going to be on the vertical axis. Now sometimes we're going to have to code switch. Sometimes we may not use x and y. Sometimes we might use time down here, say in seconds. And you have to label your graph. So your horizontal axis might be time in seconds. So let's say t would be the variable here, and let's say distance is going to go up for the amount of time that we have to run or drive a car or something. So distance will go up. So instead of y, you might have d as our variable. But whether we're dealing with x or y or t and d, just know that we are still talking about independent versus dependent kinds of variables. Now, this relationship is shown by how steep this line is. Also, we can put this kind of relationship into a table, okay? So if we were to have an x and y table, x is always going to be on the left and y is always on the right. Now, again, it might not be x and y, but the independent variable is going to be on the left and the dependent variable is going to be on the right. So all of these relationships are going to be starting at this corner of the y and the x-axis, which is going to be a 0, and we call this the origin. So all of these relationships are going to go through the origin. So the origin here is going to be at 0. So if x is 0, then y is 0. Now when you make these hash marks, you can make the hash marks however you like, as long as they're evenly spaced apart, and you choose a number increment that is going to be consistent along the x-axis. So let's say I go up by ones, 1, 2, 3, 4, and so on. Now just because I go up by ones on the x-axis doesn't mean I need to go up by ones on the y-axis. I could go up by tens if I wanted to. As long as I'm consistent with the y-axis by always going up by tens in this particular case, then that's fine right there. These scales do not have to be the same as these horizontal scales. It's totally fine. As long as you go, now you can't go up 1, 2, 10, 80. Okay, as long as you go up by an increment, you're fine. As long as you go by an increment here, you're also totally fine. Okay, so let's look at this relationship. If we buy one shirt, it looks like it's going to cost us $10. So here on the vertical axis, we're going to say this is money. Okay, so this is the total amount of dollars, $10, $20, $30, $40. So if I buy one shirt, it'll cost $10. So that's a point. If I buy 0 shirts, I'm not going to pay any money. So $0 shirts winds up with $0. One shirt winds up with $10. 2 shirts, you're going to have to pay $20. 3 shirts, you're going to have to pay 40. 3 shirts, you're going to have to pay 30, sorry. 4 shirts, you're going to have to pay $40. okay? Now, each of these points are represented in this data table. And this data table has what we call coordinates. Coordinates. Now, coordinates are an x, comma, y value with a parentheses around it. That parentheses makes it a coordinate. If there are no parentheses, then it's just a list, like eggs and butter, like you're going to the grocery store. When you put parentheses around it, it magically becomes a coordinate. So these are actually coordinates. If you think about it, I just need to wrap some parentheses around these, put a comma in the middle, and voila. This data point set can be mapped onto this graph. The x value is the left or right I go, and the y value is the up or down I go. So here I go over 1 to the right 1, and I go up 10. And I have myself a point right there. So this coordinate has an x and a y value of 1, 10. So when I plot these points, it should be in a straight line if it's a directly proportional relationship. So let's talk about what the word proportion means. Proportion means two ratios or fractions set equal to each other. So for instance, if I have the fraction 2/3, that's a ratio. To make it into a proportion, I can set it equal to 4/6. Do you see 4/6 reduces to 2/3? When I set two fractions equal to each other, then that creates a proportion. So let's say that I was making pancakes, all right? And let's say I needed 2 cups of milk for every 3 cups of flour. But let's say I wanted to make more pancakes, but I want the exact same kind of consistency of pancakes, not too thin, not too thick. If I'm gonna make more pancakes, I need to keep the same ratio of milk to flour. So I'm gonna make more pancakes, but those pancakes are gonna taste exactly like the smaller batch pancakes as well. So that's why proportions are so useful. Let's say I wanted to make a ton of pancakes. I would need to have 40 cups of milk to 60 cups of flour, and I would make a ton of pancakes, but all the pancakes would taste exactly the same. So this proportion holds true. And do you see that they all reduce to the same fraction, 2/3 in the end? So proportional relationships mean that you can take any one of these coordinates, put it into this ratio form, and make proportions out of them. That's why these are called directly proportional, because the relationship holds this proportionality to be a very constant thing. The constant of proportionality doesn't change. It's always reducing down to 2/3. Now, if there was, say, another point over here that went like this, and it kind of like, oh, and it kind of dropped off, then this would no longer be a proportional relationship at all. It only takes one point to be off of the line to contaminate the entire data set and make the entire data set no longer a directly proportional relationship anymore. It'd be called something else, but it wouldn't be directly proportional. What we're dealing with this week are just directly proportional relationships. So how do you find what that directly proportional relationship boils down to, that constant? Well, that constant, again, is always going to be either a fraction, or it could be a whole number or a decimal, but it'll be some number. So let's see what the constant of proportionality is here in this case. So this is how we do it. Constant of proportionality is this ratio that we're always boiling down to. Because constant of proportionality starts with a C, you would think that in order to boil this entire long phrase down, you would just say C. And that would be a great idea. Unfortunately, C is already taken by variables like A, B, and C in math. So C has already been spoken for. We needed some other K sound to really represent all of this. And so mathematicians came up with a K, because K is the next best thing to a hard K sound. So the constant of proportionality, instead of me saying it over and over again and having to write it out over and over and again, I'm just gonna write the letter K, okay? So K is the constant of proportionality, meaning the relationship that all of these have in common. Now, the constant of proportionality is you take your y variable and you divide it by your x variable to create a fraction. Now, this fraction needs to hold steady and true for all of these in order for this to maintain a straight line. Let's see if that happens. So k, the constant of proportionality, you always take your dependent variable. If it happens to be a y, put it at a y. Y is going to be in the numerator. And then the x, or your independent variable, is always going to be on bottom. This is a really important equation to remember. K equals y over x. Now, here, do you see that 10 is our y? Let's put it over 1. And let's move to our next coordinate. So 1 comma 10 is our first coordinate. 2 comma 20. Okay, 20 goes on top, 2 goes on bottom. Here, 30 goes on top, 3 goes on bottom. Do all of these fractions actually make a proportion? Meaning, do they actually all reduce to the exact same boiled down fraction? Yes, they do. 30 over 3 boils down to 10 over 1. 20 over 2 boils down to 10 over 1. 10 over 1 boils down to 10 over 1. So this relationship holds true. That's why these coordinates are entitled to be on this line in creating this direct proportional relationship, because they all have a constant. And what is that constant? It all boils down to 10 over 1.